Okay, so we're going to go through how to complete the Working Scientifically scaffold. And it's an investigation on Newton's second law. So we've set out to verify Newton's second law. So a suitable inquiry question would be something like, what factors affect the acceleration of a system? Okay, so we'll go on to theory, and I'm going to go through an outline of how to complete the theory component of this. And the first thing I'd do would be stating what Newton's second law is. And don't just copy what I've copied here, try and write it in your own words. So we're going to start with stating Newton's second law. Okay, as I said, first thing to do would be state Newton's second law. Then I'd write it mathematically, which is, okay, and we're going to break that down into the two parts of the investigation. So part one, or part A, we're going to look at the relationship between acceleration and net force. And we know it's directly proportional, but that's for a constant mass. And remember that this constant mass is actually the total moving mass. And what does this mean? Well, it means that if we increase the net force, then the acceleration will increase proportionally, and you'll get a linear relationship. So I'm not writing this down, I'm pretty much dictating it to you. So we've got, if the net force is increased, the acceleration will increase proportionally, and you'll get a linear relationship. And when that's graphed, it'll look like so. Okay, and in your notes, you can go on and talk about what this gradient means and how we use this gradient to get an estimate or an experimental value of the mass, and we compare that to the actual mass that we measured before we start. So we've got mass will be 1 over the gradient. Okay, so this is pretty much, it's your theory, but it also lays out the plan for the first part of the investigation. Now, if we look at part B, so part B is looking at the relationship between acceleration and the mass. And we know it's an inverse proportionality, but this is for a constant force. Okay, and again, what does this mean? And I'm dictating this. It means if you increase the mass, or the total moving mass, the acceleration will decrease. Okay, so, and that relationship is inversely proportional. And what it would look like would be that. Okay, but if we then alternatively we graph acceleration versus 1 over mass, we'll get a straight line. Okay, and from your notes, if you have a look, what does that straight line give us? Well, we get a gradient that actually equals MA. Okay, which then, of course, equals your net force. So that experimental value can be compared to the known net force that you've applied to the falling mass. Okay, so Okay, so coming back to our scaffold, what we want to now is just pretty much, it's almost the same sort of thing here. You want to write, I guess, a prediction. We've already, the theory kind of outlines the where the hypothesis is coming from. So what we want to write here is, again, you're going to have two components. So for part A, I'd write something like, for a constant total moving mass, if the net force acting on the trolley is increased, then the acceleration will increase proportionally, showing a linear relationship. Okay, so that's what we're expecting to get for part A. And for part B, for a constant net force, if the total moving mass is increased, then the acceleration will decrease, and this will show an inverse proportionality. However, if we then, however, acceleration will be directly proportional to the 1 over the mass, and that will show a linear relationship. So that's what we're expecting to find in part B. So let's move on to the variables. Now this table, I would probably merge some of these columns so we don't pretty much need that. Right, so for part A, what is it that we are changing, or what are we increasing? Okay, remember we've got a relationship, acceleration is proportional to net force with a constant mass. So what are we changing in terms of this investigation? The independent is what we measure. We're measuring the same thing each time. Okay, so you just have to put here, what are we measuring each time? It's exactly the same in part A and part B. For the controlled variables, it's pretty straightforward. Whatever you have here, it's going to be pretty much the opposite. So if we've got, say, net force is increased, then we have to make sure we control the total moving mass. And in part B, we're actually increasing the total moving mass. What are we measuring? The same. And what do we have to control? Well, if we're changing the total moving mass, we have to control the other factor. Okay, so that's all we need to put in that one. So equipment, you need to probably include everything that we had out there. So I will help you with this and rattle off a bit of a list here. So we use a dynamics trolley, which included a picket fence attached to it. We used a frictionless track, and it had the air pump as well, I suppose you can add. We had the pulley system and the strings. We used the data logger and software on the laptop, which was connected to the photo gate sensor. That was held in place by the retort stand. And we also had a mass carrier with masses, 25 gram masses. It was actually a 25 gram mass carrier and 25 gram masses. I think that's pretty much it. Okay, so an experimental setup. So if you double click on this, it opens up the drawing. You can then pretty much get rid of any of this rubbish in the way here. And use these things. Now we just want a very simple diagram, and you can just use these various shapes. So we'll say that's, and get rid of the colour. We just want black and white. So that could be the air track. Then you can have another shape, sits on top, which was the, I suppose you can make that black, that's okay, just so it stands out. You want to put on that a picket fence. Now that will be a little bit more challenging. I'll leave that with you, but it doesn't have to be perfect. I mean, if you use labels, that's all fine. We've got gradients. I don't know if that will work. No, probably not. You know, so let's, I don't know, use a different colour. And you could just label it and say it was a picket fence. We had the data logger, so we're going to, you know, make sure it comes there. Now, you don't need to draw a retort stand at all, but you want to have maybe another little shape here to represent the data logger and label that data logger, and then have another one with, you know, maybe laptop, and then you can just connect those with some connecting, I don't know, curvy, straight, who cares. So they connect pretty easily. All right, so you can connect it like so. Okay, then we've got a pulley here. Now, when you're trying to draw circles, if you hold the Shift key and then move it, it'll keep it a circle shape. Okay, and then connect that to some string. Where are we going to connect it? Oh, I don't know. Well, that's not good. We want to, again, if you hold Shift, I think it will, no, it's going to give me grief here. I'm just going to do it to there for the minute. Okay, you work that one out, or maybe, yeah. Okay, so then another string here. Shift will make sure it's vertical for me, and just put, I don't know, yeah, that'll do for your hanging mass. Okay, so that's essentially got everything you need. Then you would go about annotating that, okay, to say picket fence, dynamic trolley, air track or frictionless track, photo gate sensor, data logger, laptop, pulley, hanging mass, and then you want to duplicate this, so you're going to have two diagrams as well. So the first one, you want to annotate that you are going to be, maybe have the dynamic trolley starting with the mass of the trolley plus 5 or 6 25-gram masses attached to it. This one, you're starting off with a 25-gram mass, mass carrier. Okay, so then you need to maybe make an annotation and say that you are going to remove 25-gram mass from the trolley and add it to the mass carrier in increments of 25 grams, and ensuring that your total moving mass stays constant for part A. Then do something similar, but in the second part, you start with a fixed mass on the trolley, and you just increment and add to the mass carrier. Okay, so do another diagram and annotate what you've done there. So that's all you need to do with that one. Okay, and then when you save it, it will embed it into the document. Okay, so the procedure is probably rather detailed. I can pretty much do the first one for you, so for part A, and then you can modify that for part B. Okay, so then it'll be up to you to modify that. So I'm going to type that in. Then what you can do is maybe, I don't know, pause the video and get it down for yourself. Okay. Okay, I think that's it. I might have another look at it when I get a bit more time. So for part B, do similar, but just modify it so it suits that investigation. So we pretty much use the same equipment. The process was just slightly different. You might be able to reword it better than what I've done. in the data table, you can go to the spreadsheet. So I'll go over here and show you how I did this. So go to the spreadsheet, and we're just going to select you don't have to put the whole lot in. This is almost like you could put this in an appendix. It doesn't have to all go into the report. So we're just going to put the bits that we use for plotting. So we've got the net force. So if you select all that, press Control, and then select this column here. Now if you copy that, that can be pasted into here. So that's what I did here. I just went like so. Okay. And the same for the graph. We just have to go into the document. You can't right click if you go to do that. You just have to press it, go Control C, and trust that it's copied it, and then come back in and paste it here. Okay, you can keep it linked to your spreadsheet if you're using your own spreadsheet. I think you've all got a copy of the spreadsheet. Let me know if you don't. So paste it. Okay. Okay. All right. So now I will leave it at that. You can go on and have a go at talking about, trends, patterns, relationships from the data. And well, we can talk about that later. So for the calculations, I don't expect you to do the calculations, but I would expect you to be able to explain how they were done. The graph automatically does the gradient for us, but I want you to talk through, going back to the theory, how we came to those values. Okay, how would you do it manually? Actually, I think you can go on and do accuracy. So have a look at that. What are we looking at for accuracy? To assess the accuracy, we can use those gradients and the values we calculated from them to, compare it back to what we're expected those particular values to be. For example, in the first one, the total moving mass, well, we put that on the balance and worked out what it should have been, and then we compared it to the experimental mass, which we got from 1 over the gradient. Okay, so you compare that, look at the percentage difference, and write a comment here. So it's going to be similar when you're assessing it. It's going to be similar to make a claim, show me your evidence, and then do the reasoning. So in terms of reasoning here, accuracy, I would define accuracy and say accuracy is a measure of how close an experimental value was to an expected value. Your evidence of how close it was is based on your percentage difference. So if it's close, then you make a claim that it was, quite an accurate investigation, which I think ours wasn't too bad. Is there room for improvement? Can we improve that? To improve accuracy, you have to minimize any systematic errors. The systematic error in this case will likely be friction. So what we've done, we've actually minimized friction as best as we can. It's been impossible for us to remove it. However, if the expected and experimental weren't close, you'd have to figure out a way to minimize that effect. Okay. Reliability, well, that goes again the same way, that we make a claim, we give the evidence, and we use reasoning. And I would start your reasoning with what the definition of the reliability is. So it's how close those measurements are to each other and to the average. If they're close, and also if you look at the graph, if the plots fit nicely to the line, then you could make a claim that you've got reliability. And again, think about how you might improve reliability. Line of best fit, just have a look at that one and answer that question. Well, okay, I can come back to that one. Validity is, again, how do we go about controlling variables and keeping them constant? So the equations wouldn't hold if you didn't control all those variables. So if we, things like if the ramp wasn't leveled, or if there was friction between the string and the pulley, or if there's friction along the track even though we've got the air pump. So all those things, it's all about validity, is about controlling those variables. And so in this one, you can say that you did, in what ways do we try and make sure all those other factors are controlled. Okay, that's enough.